Welcome to episode 121, Spotlight Flaw Remediation, focusing on Control SI-2. Every system accumulates weaknesses over time, some discovered through testing, others revealed by attackers. Fixing these flaws quickly and predictably is a core element of operational security. Unpatched vulnerabilities are open doors that grow wider with age. Flaw remediation requires both speed and structure, balancing urgency with safety. When done right, it turns security response into routine rather than chaos. The measure of maturity is not whether flaws exist, but how swiftly and reliably they are identified, prioritized, tested, and closed. Building from that foundation, remediation starts with disciplined intake from multiple sources. Scanners, vulnerability advisories, bug reports, and penetration tests all feed into a unified process. Each input provides a different angle. Automated tools highlight technical exposures, advisories describe new exploits, and human testers uncover logic flaws. Combining them prevents blind spots. For example, a web application scanner may flag an outdated library, while a penetration test finds an insecure workflow. Treating all inputs as signals within one queue eliminates fragmentation. Flaw intake becomes a living radar, detecting weaknesses early across both infrastructure and applications. Defined remediation windows then translate priority into action deadlines. Critical issues might require fixes within 72 hours, high within a week, moderate within 30 days, and low within a quarter. These windows should be formalized in policy and measured rigorously. They give teams clarity and management visibility. For example, an enterprise patch policy might demand that any remotely exploitable vulnerability be mitigated within 5 business days of confirmation. Predictable timelines transform vague urgency into measurable commitment. When everyone knows the clock starts at detection, the organization moves as one coordinated body toward closure. Temporary mitigations fill the gap when permanent fixes cannot yet deploy, but each must carry an explicit expiry date. Mitigations may include disabling vulnerable features, tightening firewall rules, or isolating systems until patches are ready. For example, blocking a specific port or disabling a plugin buys time to test official updates safely. However, mitigations are stopgaps, not destinations. Each requires documentation, approval, and revalidation until the root cause is corrected. Expiry dates prevent temporary controls from becoming forgotten fixtures, ensuring that mitigation remains a bridge to resolution, not a substitute for it. Before patches or configuration changes reach production, they must undergo controlled staging, testing, and rollback rehearsals. Testing ensures fixes resolve vulnerabilities without creating new faults or breaking functionality. Rollback rehearsals guarantee recovery paths if deployment fails. For example, a team might clone a production system into a sandbox, apply the patch, validate operation, and document reversion steps. Skipping testing turns remediation into risk migration, trading one problem for another. Staging and rehearsed rollback protect uptime while enabling decisive remediation. Fixing securely means proving stability as well as closure. Change approvals should scale proportionately with risk and urgency. Low-risk patches can follow expedited or automated paths, while high-impact updates, like kernel or database changes, require deeper review. Proportional approval prevents bottlenecks without sacrificing oversight. For instance, a critical zero-day patch may bypass routine scheduling under emergency authorization, while a routine library update follows standard review. Embedding risk-based gating keeps response nimble yet accountable. Governance is not obstruction. It is structure that ensures traceability and prevents hasty, undocumented fixes from introducing new instability. Verification rescans and closure proofs complete the remediation cycle. After each fix, scanners or manual tests confirm that vulnerabilities no longer appear and that mitigations remain intact. Closure records should include timestamps, responsible individuals, and validation evidence. For example, a closure note might cite rescan ID, severity change, and approval signature. Without verification, fixed becomes opinion rather than fact. Independent confirmation turns completion into confidence. Verification closes the feedback loop, proving that remediation achieved its purpose rather than merely being attempted. Exceptions arise when flaws cannot be fixed immediately due to dependencies, business constraints, or vendor limitations. These exceptions must be documented, justified, and paired with compensating controls. Compensations might include network isolation, increased monitoring, or use restrictions. Each exception should include a reassessment date to ensure ongoing visibility. For instance, an unsupported operating system awaiting replacement might receive a waiver valid for 90 days, with proof of isolation and enhanced logging. Exceptions manage reality without surrendering discipline. Transparent documentation converts delay from negligence into managed risk. Coordination with third parties and providers ensures consistent remediation across shared responsibilities. Cloud platforms, software vendors, and managed service providers must receive timely notice of discovered flaws and confirm their patch timelines. Contracts should define communication procedures for vulnerabilities that affect multiple tenants. For example, a vendor supplying embedded firmware should share patch status within agreed intervals. Collaboration closes external gaps that internal controls cannot reach. Supply chain coordination ensures that the organization's security posture does not stop at its firewall, but extends through every trusted partner. Communication with users about outages or impacts builds trust during patch cycles. Scheduled maintenance notifications, transparent explanations of urgency, and clear timelines reduce frustration and speculation. When a security patch temporarily disrupts service, explaining why it matters demonstrates professionalism. For instance, alerting users that downtime protects against active exploitation reframes inconvenience as prevention. Communication transforms disruption into shared responsibility. Silence breeds suspicion. Openness reinforces partnership. Effective flaw remediation includes people, not just systems. Metrics make progress visible through backlog size, remediation velocity, and service-level agreement adherence. Backlog measures open vulnerability. Velocity tracks closure rate, and SLA adherence confirms deadlines met. Trends reveal whether the program is catching up or falling behind. For example, cutting the average closure time for high-severity flaws from 10 days to 4 shows maturing capability. Metrics turn an endless task into measurable success. Data-driven insight keeps management engaged, focusing effort where it will reduce real-world exposure the fastest. In conclusion, Control SI-2 defines flaw remediation as a disciplined, rhythm-detect, prioritize, fix, verify, and document. Fast, predictable closure matters more than panic-driven speed. Structured remediation restores confidence each time a weakness surfaces, proving that security is not perfection but responsiveness. When every flaw follows a clear path from discovery to validation, the organization gains both resilience and credibility. In the end, predictable closure beats heroic firefighting every time. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.